Yeah, so thank you very much. I just sort of wanted to start off with some thanks, not only for the opportunity to speak, but maybe even more so for something to speak about. So yeah, as Evan mentioned not too long ago in this very seminar series, Bob Kleinberg from Columbia and from Boston talked about the global warming potential, and we sort of spent the whole hour railing about against this metric. Bob and I have been colleagues and neighbors for over a decade, and he has told me about his work here many times. So of course, it took until this meta seminar for me to get this idea through my thick skull about what the heck he was talking about. But it was that understanding of all the kind of drawbacks of GWP that led to this project, which tries to come up with an alternative that addresses at least most of the drawbacks that Bob mentioned. Okay, so I think most folks are familiar, but just as a quick introduction, GWP, the global warming potential, is the one number that is used to convert from a mass of your favorite greenhouse gas to an equivalent mass of carbon dioxide. It's particularly relevant for greenhouse gases that don't live in the atmosphere as long as CO2 does. And for methane, there are numbers that I think are familiar to most. The global warming potential for methane averaged over a 20-year period is 84, and evaluated over a 100-year period is 28. I will point out that these numbers have changed over time. So here is a little history on how things have changed. This is the 20-year and 100-year GWP for different versions of the IPCC assessment report. Some of these initial changes reflected advances in the understanding of the physics of global warming. And now folks are thinking about maybe adding some other feedbacks or some other physics referred to as carbon feedback. And then I want to point out that GWP, although it's the most common, is one of many metrics. Here is a dozen or so other numbers that are kind of like GWP. And just sort of quickly on the difference here, when you think about the impact of emission, you have to kind of model what your default emission is. In some cases, you model it as a pulse emission. So that would be good if you're thinking of something like in the Aliso Canyon blowout when you got a whole bunch of greenhouse gas coming out at the same time. Or you can model it as a sustained emission. That'd be good if you're thinking about like building a power plant where you're going to have an emission coming out, year by year for many years. You can also model things in terms of radiative forcing. So if you think about global warming like putting a blanket on the planet, the radiative forcing tells you how thick that blanket is. So if you have a pulse of emission, you've got a thick blanket, and then that thing is going to get smaller and smaller as time as the methane is removed from the atmosphere. Another way to look at things is the temperature change. So that's like, if you get into bed, you put a thick blanket on, you don't get warm right away. You need a little while for the temperature to increase. So temperature change is one that sort of goes up over time and tells you really about how this greenhouse gas emission is going to cause the Earth's temperature to change. Okay, so there are a lot of metrics. The most common one is this global warming potential. And as Bob explained to us quite elegantly, we all love to hate the global warming potential. So I thought I would summarize his talk here, where I would go over what would be a typical experience of somebody who actually wanted to use the global warming potential. So in this typical experience, you say, well, I need a single number that's going to help me go from methane to CO2. And that's great. That's what GWP is supposed to do. Okay, if you want to use it, you got these two choices, the 20-year or the 100-year. You got to pick one. Okay, so we know that the 20-year time horizon, that more or less represents the short-term effects, and the 100-year time horizon more or less represents the long-term effects. But with that understanding, this selection is still kind of arbitrary, right? I mean, how do you know if 20 years is better or 100 years is better? Or why are the numbers 20 years and 100 years and not 10 years or 300 years? And when you think about other things that have impacts further out in time, you don't too often think about that in terms of choosing, to integrate over 20 years or to evaluate over 100 years. So you got to make this choice, but you don't really know how to make it. What you do know is that the choice you make has a really big impact on your conclusions because the 100-year GWP and the 20-year GWP differ by a factor of 3. So for scientists and engineers, this is the kind of thing that makes our skin crawl, right? Because there's a choice that we know is not well constrained, but has a very large, in this case, a factor of 3 impact on the conclusions that we come And then there's this other part of the experience, and maybe this is less common, but there are these things that matter. There are these different metrics that have pulsed emissions or sustained emission, this sort of thing. And at the end of the day, if you want one number to compare between these two gases, you need to pick which one of these things to choose from. So as an example of this experience, I thought I would talk about sort of the most fundamental question that this community often thinks about is, how important are oil and gas methane emissions? So for a few glorious moments last week, we thought we were going to get a presentation on this exact subject in this seminar, which turned out to be Evan's sick idea of an April Fool's joke, but we can go over it here. Okay, so if you wanted to answer this question, at least the start is pretty easy. You go to the IEA's website, and IEA says that the oil and gas industry emits 0.72 billion tons of methane a year. Now, billion tons of methane a year does not mean very much to very many people. So we'll convert that into CO2 a year. We'll use the global warming potential. So if you're a GWP 20 guy, you'll multiply by 84, and you'll say there's 6 billion tons of CO2e per year. And if you're a GWP 100 kind of guy, you'll multiply by 28, and you'll say there are 2 billion tons of CO2e per year. Okay, I think billion tons of CO2e per year is a little bit more meaningful, but just to kind of drive home the point, here is a plot showing the world's CO2 emissions broken down by continent and evaluated over a couple hundred years. So if you're a GWP 20 kind of guy, you'll use this 6-ton number, and you're going to put oil and gas methane emissions here. Notice that the oil and gas methane emissions are above Europe. So if you wanted to, you would be totally justified in saying that global warming from methane emissions from the oil and gas industry is more significant than global warming from the entire continent of Europe. I think that is, the data totally support that. That's a justified thing to say. On the other hand, if you're a GWP 100 kind of guy, you're gonna go for something that's a factor of 3 less. So I will say our community's inability to decide on which of these numbers we want to use leads to our inability to articulate if the thing that we're talking about is like a continental scale kind of problem or is something less. So what we'll hope to do now is try to improve on that situation by giving us a better way to make this decision, a better number to use. Okay, just briefly, having beat up on GWP like people are wont to do, a little bit of explanation as to how this is calculated. What you do is you take the quantity that you're looking at, which changes over time. These numbers are pretty easy to look up. In this case, what I have chosen is I have chosen to look at the temperature increase, not the radiative forcing. And I've looked at a sustained emission duration, not a pulse. I will point out that the actual GWP has different choices. This is one of these other ones with one of these other names. But what I really want to focus on is how these things are evaluated over time. That's really the crux of the talk. And that's the same for GWP and all these other metrics. So in this case, this is the temperature going up as we emit greenhouse gases. When you emit methane, remember the Earth has a pretty reasonably fast process to remove methane. So as we put methane up, some methane comes out, and at some point you achieve kind of a steady state. For CO2, there is not an effective way to remove at least all of the CO2. So things don't really level off. They kind of keep going up. And when you calculate the GWP over like 100 years, or any of these metrics like GWP, what you're going to do is you are going to integrate these things over 100 years. So you're going to say, I'm going to care about the effect of this greenhouse gas over 100 years, and I'm not going to care about anything afterwards. That is outside of my integral. Okay, so why do we do that? Why do we integrate over 100 years, or instead of a different amount of time? Why do we integrate over the first 100 years instead of the second 100 years, or how do we make this choice? So I thought the best way to explain this is to go back to what's referred to as the Stanford marshmallow test. So this was designed by a couple of psychologists at Stanford. And what they did is they took a kid this age and they asked him, would you like to have 1 marshmallow now or 2 marshmallows, but you got to wait 15 minutes? And they put the marshmallow on the plate And they said it right in front of this kid who has this kind of look of he's really got to make this decision here, trying to understand if he wants one now or if he can wait a whole 15 minutes to get a second marshmallow. Now, when you're an adult, maybe waiting 15 minutes is not so hard. We have a little more patience, but that's really difference in degree. The concept is the same, both for kids and adults. We prefer things now. It is human nature to value the present more so than we value the future. And really there's a question of degree. Maybe for kids, they value the present much more than the future, and adults only a little bit more in the future. But we always value the present, at least to some extent, more than we value the future. And that's why GWP, you integrate for, let's say, the first 100 years. You consider the 100 years to be the present, and I guess we'll say, near future. And then things beyond that are the far future. So you care about the kind of the present, that thing you consider. The far future you don't care about as much, so you don't worry about that. Okay, so another way to think about the way that this GWP is computed is to think about it as a weighting function. So this is the amount of weight that you assign to your effect in these years. For GWP, it's a stair-step function. The first 100 years are in the integral. They're all in there. There's no other weighting function. You don't care about year one more than year two or anything like that. They're all weighted the same. So you've got a weight of 1 for the first 100 years. And then it drops to 0 after that, because after 100 years, you're kind of outside the integral. So these are things that make no impact in your computation for GWP. Okay, so so this is a weighting function. So let's think about if this is kind of a reasonable one or not by asking a couple of questions. So you can say to somebody in this weighting function, would you like a marshmallow now, or would you like a marshmallow in 100 years? And the answer is, well, I kind of don't care, because I value things now and I value things in 100 years at exactly the same. They both have this weight of 1. So it kind of sounds ridiculous. I mean, you can ask yourself, would you like to receive your paycheck, every 2 weeks or whatever, like you normally do, or would you prefer to work for free and get your paycheck 100 years from now? Kind of obvious what the answer to that should be, but GWP has kind of this unusual thing where you evaluate year 100, you weight that as highly as you weight today. So then you can ask, would you like a marshmallow in 101 years? And the answer is just no. So it kind of feels like maybe I didn't get to ask the whole question, but I did. I'm not asking, do you want a marshmallow in 101 years or something else? Just, would you like a marshmallow in 101 years, yes or no? And the answer is no. Your weight at 101 years is 0. You really don't care if you get something, you don't care at all what happens in 101 years. That's another kind of unusual thing about the GWP weighting function. And then you can ask, what the heck happened at 100 years, right? How do you go from caring about things intensely, caring about things in year 100 as much as you care about things today, to overnight dropping down and caring about things not at all? What the heck happened right at that time to cause your valuation to change over such a large extent? Okay, so these are kind of 3 things in the GWP weighting function that are all kind of ridiculous. And as we try to come up with a better metric, we're going to try to use a better weighting function. So the more normal weighting function that people use is what is called the discount rate. And the formula is over here. Your weighting function in a future year is given by 1 plus the discount rate to the power of negative time. So essentially these curves look like this. And what the result is that every year you knock a little bit off your weighting function. Every year you weight things a little bit less than the year before by an amount equal to the discount rate, which is usually something like a couple of percent. So if your discount rate is rather small, then this curve is rather flat because you're only knocking off a little bit each year. But if your discount rate is big, then this curve is rather steep because every year you're knocking off a pretty good chunk. So there are different people and they have different discount rates based on how they value the future compared to the present. But this is a pretty reasonable way to go after it. And you can kind of ask this the same basic questions, right? Would you like a marshmallow now or in 100 years? Well, you'd like one now better, right? The weight is always higher today than it is 100 years from now. All right, so that makes some sense. Would you like a marshmallow in 101 years? Yes, please. I mean, rather take it than leave it. Maybe don't care so much that the discount is pretty heavy. The weight is not that high, but it's at least greater than 0. You'll take a marshmallow for free rather than pass it up. So, okay, that makes some sense. And what happened at year 100? Nothing, right? This is a smooth curve. There is nothing unusual, nothing out of the ordinary that takes place in year 100. So these are 3 things that are kind of more reasonable about this discount, this weighting function than the GWP weighting function. And in fact, this weighting function is actually pretty common. It's used in economic analysis to compute something called the net present value. So I know not everyone on the call today is too familiar with economics, and some folks may not have heard of this, so I'll kind of explain what this is. The net present value, the NPV, is a single metric that incorporates both short and long-term effects at the same time. And it does that by weighting future effects according to the discount rate. So you discount things in the future based on how much less you care about the future as described by your discount rate. What is valuable about this is that it's a decision-making tool, because it's a single number that incorporates both the short-term and long-term effects. It does that appropriately, and it really allows you to evaluate short-term and long-term things at the same time. So I thought it would be most valuable to go over this by way of an example, and I'm going to talk about an example that's very personal to me. So I live in a house in the suburbs of Boston, and I'm trying to figure out if I should put solar panels on top of my roof. So as we like to say here, what Massachusetts lacks in sunshine, we make up for with very generous policies for residential rooftop solar. So if I think about this, I'm going to ignore the environmental consequences for now, and I'm just going to think about this as an investment. I'm going to think about the cash flow. And the cash flow is this. Right away, I pay 20,000 bucks. That's the amount I have to pay to buy the solar panels, less the incentive I get from the government. And then every year, I make 4,000 bucks a year. That's a combination of the electricity that's generated plus the good old state of Massachusetts incentive. And that's going to happen for 30 years, which is the lifetime of the solar panels. So my question now is not, am I looking at the short-term or long-term effects, right? With the GWP, you kind of choose, are you going to look at the short-term or are you going to look at the long-term? That's not what we're talking about here, right? Here we're looking at short-term and long-term at the same time. We have perfect information. We know exactly what the cash flow curve is going to be. The question is this upfront investment worth it? Is it worth it to me to pay 20,000 bucks now in order to make 4,000 a year? Okay, so if you're going to do this GWP style, well, you're going to count every year the same. So you're just going to add this up. You're going to add up your -20 the first year, and then 30 years at 4K, and you're going to get a nice big positive number, and it's going to tell you that, yes, absolutely, this is an investment you want to make. But again, this is a kind of ridiculous way of looking at it, because this involves treating your dollar in 30 years and weighting that the same as your dollar today. And nobody thinks that a dollar in 30 years is worth the same as a dollar today. So this is a nice and simple way to do it, but not a very realistic one. The more common way to do it, so the way an economist would do it, is that you take this cash flow curve, you would multiply it by your weighting function, your discount curve. And I've been a little lazy here. I've shown this one out to 200 years, but really it's only the first 30 years that matter, because that's the lifetime of the solar panel. You would multiply those two things together, and you would get your discounted cash flow. So if you look at this, okay, today, we're not going to discount today because today's today, today's not in the future. So they're always at negative 20K. But then in the future, where we used to be when we were undiscounted, we were always at 4. Here we go down a little bit every year. And the amount we go down is determined by our discount rate. If our discount rate is small, that's in the blue, we're only knocking a little bit off. If our discount rate is large, that's in the yellow, we're knocking down a lot. Now that we have our discount rate, so we've treated the 4K that we're going to get in 30 years appropriately by knocking it down by how much we care less about 30 years than we do today, then we have something where we can add all these up. We add up the discounted cash flow, not the straight cash flow, but the discounted cash flow, and we can determine the NPV, and we can figure out if this is a good decision or not. Again, if your discount rate is low, then this thing is going to look pretty good because you're only knocking down this revenue stream a little bit. If your discount rate is high, this investment looks worse because you're knocking down your future revenue more. But at the end of the day, kind of like what we're hoping for, this is a single metric. There is one net present value. If you have a discount rate, if you're a different person with a discount rate, you may have a different NPV, but each person with their discount rate, they have one NPV. It incorporates both short-term and long-term effects at the same time. It appropriately weights things in the future according to this discount rate, which is the pretty reasonable way to evaluate things in the future, unlike the kind of step function that we talk about with GWP. And that it allows you to make the decision. So it's not just, are you presenting short-term or long-term, but really what do you do with that information and how does it allow you to make that decision? Okay, so if we use that to, we can now do the same thing to think about what's going to happen in the future with climate change and how we evaluate methane. And that is where we want to introduce this term that we now call the present global warming. So this is supposed to be like the net present value, but now it's present global warming. The word present means we take effects in the future and we put them on today's scale because we discount them according to the discount rate. I've dropped the word net. Net was useful in this case where you had some negative terms and some positive terms, but here, we're only talking about positive numbers, so we don't need the net anymore. And of course, we're talking about the global warming instead of the value. So this is not net present value, but it's present global warming. So the way this is computed is you start with this same effect versus time curve, the same curve that you started out when you were using the global warming potential. You now weight things in the future according to this normal exponentially decaying a discount function. And you multiply those two things together to get the discounted, in this case, the discounted temperature increase. So to look at the shape of these things go up in the beginning because remember, we're looking at the temperature change here. And so as we get into bed and put the covers on, the temperature starts going up. Then at the end, these things curve down. That's because the temperature is increasing linearly. The discount is falling exponentially. So the exponential wins and this thing falls over and turns down. We've got curves for CO2 and we've got curves for methane. At low discount rate, these things tend to go higher and peak later because you're not knocking down the future as much. As you go to higher discount rate, like in the black, the peak is lower and pushed to earlier because you're now discounting things in the future. So now you can do the same thing that you did for GPW. You take these curves, you integrate them over time, and you divide the methane curve by the integrated methane number by the integrated CO2 number, and that is your PGW. That is your present global warming. Okay, so if we think about the benefit of this, we can kind of go about this typical experience and see how is this going to be different with PGW. So it used to be you needed a number to convert from methane to CO2, and still, that's the goal here. We need a number to convert from methane to CO2. It used to be you'd have to choose between the what time horizon, how many years. Now you got to choose your discount rate. It used to be that you could pick either the short-term one or the long-term one. You could present the short-term effects or you could present the long-term effects. And this is an improvement. Now we're incorporating both the short-term effects and the long-term effects at the same time with this value where we've discounted the long-term effects appropriately according to the discount rate. So I think this is one advantage of the PGW. But I think the question that you should be thinking about now is you say, well, if you want to do this, it used to be you had to choose a number of years for GWP. Now you're going to have to choose a discount rate for PGW. Is this really helpful? How is your choice of discount rate any more informed than your choice of number of years? So it turns out that choosing discount rates actually is not that hard. Because economists have been doing things like calculating NPV for 100 years, there is a lot of literature on what is the appropriate discount rate. In fact, there are a lot of publications on discount rates that are used for environmental things like computing the social cost of carbon. There is a range here. Folks from different organizations have chosen different things, but there are some pretty popular numbers. So a 3% discount rate has been used for this kind of thing by the George W. Bush administration. It is being used, at least so far, being used in the Biden administration. It was the base case scenario for the Obama administration. Obama was a little bit more thorough about it and also included sensitivities at a little bit lower and a little bit higher discount rate. But this 3% discount rate seems to be a pretty commonly accepted choice for looking at exactly this kind of thing, looking at environmental things. I will point out that one former presidential administration did things a little bit different, and that had some interesting consequences. But the advantages where before you had to choose things arbitrarily, right? How do you know if you want to think about things from 20 years or things from 100 years, and why 20 or 100 and not 50 or 75? We have no experience or not much experience thinking about future effects with this kind of integrating over a certain number of year thing. That's really not the case here. Here you can choose, so you do have to make a choice, but you can use that choice the same way you've chosen other things. In fact, you might as well just use the same discount rate that you're already using for your other similar calculations. Okay, so now instead of choosing short-term or long-term, you get short-term and long-term at the same time. Instead of making this choice that's kind of arbitrary and not really knowing which number to choose, here, well, you at least have some guidance. You can choose the number people have chosen before, or numbers things like your presidential administration uses to do other calculations that similarly look at future effects and try to compare long-term and short-term effects. But another thing you can do is do a little bit of a sensitivity analysis and try to understand how impactful are these different choices. So to address that, let me just show you the weighting curves that we're talking about here. So here's the GWP curve weighting function for 100 years and for 20 years, right? There are these two steps, and the steps at 20 or 100. And just notice how different these things are, right? For the 100-year, most of the time, right, there's this 80-year period where the 100-year GWP is at the maximum possible weighting and the 20-year GWP is at the minimum possible weighting. And this is kind of at the root cause thing. The reason that the 20-year and the 100-year GWP are such different numbers is because the weighting curves are so different. The orange curve and the blue curve look so different from one another. On the other hand, the PGW weighting, the curves kind of look all the same. They're not exactly the same, but they all have the same exponential shape. They're all biggest in the first year and they all go down after that. They all have the same, they all have pretty high weights for the first couple of decades. Really, where they chart us to spread out is in these later years. And as it turns out, because methane disappears from the atmosphere on the order of 12 years, CO2 is multi-exponential, but one of those timescales is 4 years and another one is 36 years. And those two averaged together are pretty close to 12 years. A lot of the action for the first couple decades for methane and for CO2 is about the same. So you see the methane curve and the CO2 curve more or less track each other for the first 20, 25 years. Where they start to diverge is where your weighting functions is already pretty low. So it turns out that the actual PGW number you get is not that sensitive to what discount rate you choose. For these discount rates, here are the numbers that you get. For this base case, is 3%, you get a number of 55, and then it varies between 50 and 70 or so, maybe up to 80 if you're going to go Trump administration on us. But compared to this factor of 3 variation that we're talking about for different GWPs, here we have a much smaller range. So now you can choose something that incorporates short-term and long-term at the same time. You kind of know, you do have to make a choice, but you kind of know which number to choose because it's, you can just use the same number you've already chosen for other things. And if you want to choose different numbers, well, that has some effect, but it turns out really not that big of an effect. Okay, and the last thing I wanted to hit is the kind of these sort of lesser considerations about whether you want to model a pulsive emission or a sustained one, or you want to look at the radiative forcing or the temperature rise. If you do this for what I call GWP-like metrics, these are metrics where you're going to integrate for 20 years or you're going to integrate for 100 years, here's what you get. There are metrics where you look at radiative forcing or temperature, whether you look at pulse or sustained. Folks have come up with different names for those different metrics. Here are the numbers. Over 20-year span, they don't change that much, but on the 100-year time horizon, there's like a 50% difference between the lower value and the higher value. So although GWP is the more common one, you kind of do have to make a choice about, do you want to think about sustained emissions or pulse emissions, and do you want to think about temperatures or radiative forcing? And there are plenty of academic papers arguing for the pros and cons of pulse versus sustain or temperature versus radiative forcing. As it turns out, for the same reason we talked about before looking at the different discount rates, in the PGW-like metrics, where you discount not with a step function, but with the exponential function, these things don't hardly make any difference. Whether you look at pulsed or sustained or radiative forcing or temperature, the factor you use is basically always the same. They varies with discount rate a little bit, but it really doesn't vary with these kind of choices. So then, kind of putting this thing together, now even this maybe lesser choice about pulsed or sustained, which used to impact the GWP, really doesn't impact the PGW. So this is kind of my last slide and sort of wrapping things up. If I compare the GWP and the PGW, they are both one number that allows you to convert from methane to CO2. They both have an adjustable temporal parameter, whether it's a number of years or it's a discount rate. But where you have this drawback that the GWP allows you to make this choice, do you want to describe short-term effects or long-term effects? PGW has the advantage that you can incorporate short-term effects and long-term effects at the same time in the way that you normally incorporate short-term effects and long-term effects at the same time when you want to do things like making an investment decision to see if your spend today is worth it to get your revenue tomorrow. So in PGW, where you have to choose between long and short, this is kind of an unfamiliar and sort of arbitrary choice. Why is it 20 and 100, or why isn't it something else? And how do you think about these? In PGW, this is a familiar choice because you're thinking about things in kind of the same way people think about future effects. Otherwise, you can use the same discount rate that other folks are using to think about the same kind of issue. It turns out in this choice, for GWP, you don't really know how to make the choice, but you do know that your choice has this pretty big factor of 3 impact in your conclusions. For PGW, not only do you kind of know how to make this choice, but it turns out if you want to change things a little bit, if a new administration or something like that has a slightly different discount rate, that really is not going to impact the PGW very much. The sensitivity is low. And finally, similarly, this kind of emission you're looking at and the duration of that sort of thing, which has a reasonably large impact in the GWP, has a very small impact in the PGW. So then the recommendations here is, we've introduced this new metric that we call the present global warming, PGW. I'll say this improves on at least some aspects of GWP. Not to say the PGW is a perfect metric, but there are a few things about GWP that we've complained about in the past, and I think we've at least improved on them here. As far as I know, we haven't made anything worse. At least I haven't yet found anything about PGW that's more arbitrary or more sensitive than it is for GWP. So really, at the end of the day, my recommendation is going forward, where possible, when you need a number to relate methane to CO2, that number ought to be a factor of 55. That is the PGW at the pretty common discount rate of 3%. And if you're interested in evaluating things over different discount rates, you can do a sensitivity analysis, but the sensitivities aren't going to be that bad because basically for all normal discount rates, PGW is pretty tightly constrained to be within a factor of 50 and a factor of 70. So that's what I got so far. Thanks a lot for listening to me talk for a little while about this new metric. Thanks again, Evan, for the invitation, and I'm happy to take any questions.